Hello everyone, my name is Federico Renda and I'm recording this video to present you our work for the IEEE International Conference on Soft Robotics, RoboSoft 2020. The title of our work is A Geometric Variable Strain Approach for Static Modeling of Soft Manipulators with Tendon and Fluidic Actuation. This work has been conducted in collaboration with the EMT Atlantique of France and the Aix-Marseille University in Marseille, France. The reference for this presentation are mainly two: the manuscript of the conference paper published in the IEEE Robotics and Automation letter, and a preprint currently submitted to the IEEE transaction on robotics that can be found in the HAL archive at this web link. One of the main challenges for the development of soft robotics is its modeling aspect. Modeling of soft robot is a very active research area that has produced a lot of outcomes so far. Probably the most popular and commonly used model for soft robots are the constant curvature approach and the 3D finite element method, among others. In this presentation, we will present a strain-based approach that has many advantages in our opinion. Some of them will be illustrated in more details later on in this presentation. But what is probably the main feature of this approach is that it can be considered as a natural extension of the geometric approach applied to rigid link robots, or in other words, the same theory that we are going to present you, once applied to rigid link robot, become the traditional geometric approach for this class of robot. In this presentation, Lie group notation are used. So position like variable are element of the special Euclidean group, while velocity variable and strain variable are element of the Lie algebra of the special Euclidean group. Adjoint representation of the group and its algebra are also used to act on strain variable and velocity variable. Our geometric strain approach is based on the continuous cost-error theory that we recall briefly here. The continuous kinematic relate the configuration of every cross-section with the strain. Continuous compatibility equation relate the twist velocity of the cross-section with the strain again. While taking the equilibrium of a section of an elastic rod and limiting the length of the section to 0, we obtain the partial differential equation describing the rod dynamics that are expressed here. Note that the actuation is an internal force whose range can be expressed in this form, where d is the distance of the actuator to the midline, t is the tangent vector to the actuator, and tau is the actuator strength. Let's start with the kinematics of our geometric strain approach. First of all, we divide the robot arm in n pieces of variable strain that correspond to the element of a finite element method. The continuous strain field is parameterized by a finite set of interpolating function and interpolating node. Then the configuration of the manipulator can be integrated from its continuous kinematic using the Magnus expansion. This allows to express the configuration of the manipulator with respect to the finite state variable q, our interpolating node, through the product of exponential formula. It's interesting to note that the product of exponential of rigid link robot can be obtained as a special case of this product of exponential. The continuous compatibility equation is a linear matrix differential equation that can be analytically integrated using standard technique. This produces an analytic formula for the geometric Jacobian that relate the velocity twist with the time derivative of our state variable. The time derivative of the velocity twist produces also an analytic formula for the time derivative of the geometric Jacobian. With those kinematic tools, we can obtain the generalized dynamic equation by projecting the Koseral rod dynamics onto the constrained motion space described by the Jacobian. Doing so, we obtain the generalized dynamic in the Lagrangian form, which can be solved for Q. Then the manipulator configuration can be reconstructed using the minus expansion and the product of exponential. In this slide, the coefficients of generalized dynamics are shown in greater details. I would like to draw your attention to the generalized stiffness and actuation metrics that are simple block diagonal metrics depending on the interpolating function. This is thanks to the Jacobian projection that analytically integrate internal force. We validate our approach through dynamic numerical tests that are reported in the preprint of the paper submitted to the TRO. The first test is a clamped beam roll up and release, which allow us to verify the convergence of the solution for a polynomial basis of increasing order. The second test is a zero stiffness continuous pendulum swinging in gravity that allow us to confirm that our model is able to compute dynamic motion without the support of any constitutive law. The third test is an internally actuated floating beam in vacuum that verify the conservation of the momentum. Now I would like to draw your attention to an interesting result that is reported in the conference paper. Consider the static equilibrium of an actuated manipulator without external forces. In this condition, this specific choice of the interpolating function, which involves the elasticity of the rod and the actuator geometry, yields to the simplest form of the static equilibrium, Q equal to tau. Then, substituting those results in the reconstruction equation for the strain C, produce this simple model, which is a concise and yet accurate interpretation of the relationship between the actuator force, tau, and the robot arm deformation, Xi. Remarkably, this model, which is a nonlinear algebraic equation, can be solved for the strain Xi for any x independently. Then, as in the other cases, the manipulator configuration G can be reconstructed using the minus expansion and the product of exponentials. We compare the trivialized model against the generic geometric strain approach and the traditional continuous Koseral model. In this first test, we consider a cylindrical manipulator with linear path actuators. In other words, the distance of the actuator with respect to the center line as a linear coordinate in the local frame. In this first example, we consider linear actuator with a constant distance to the midline, which produce the well-known constant curvature shape, which is well captured by all the three models. In a second example, we consider still linear actuator, but with an oblique path, which intersect the midline. In this case, again, all the three models are able to reproduce the symmetric shape in the same way. However, it's interesting to note that although the curvature is linear, the elongation is not linear, and this is well captured by the continuous Koseral model and the trivialized model. In this third example, we have multiple linear actuators with different 3D paths inside the manipulator. Again, in this case, the curvature is linear, however the torsion is not. Although for this example, this non-linear torsion is well captured by a linear discrete basis. In this second test, we consider cylindrical manipulator, but with helical path actuator, or in other words, the distance d of the actuator to the center line of the manipulator as sinusoidal coordinate in the local frame. In this first example, we consider only one helical actuator, and we notice that sinusoidal base function correctly represent curvature, the two curvatures, while torsion and elongation are practically constant. In the second example, we consider two helical actuators with different pitch, and again a combination of sinusoidal function of the two pitch are able to represent the curvature, the torsion, and elongation in this case. In this third and last example, we consider conical manipulator with linear and helical path actuators. To highlight the difference between the trivialized model and the generic geometric strain approach, the prescribed basis of the generic geometric strain approach has been kept identical to the case of the cylindrical manipulator. In the first example, we consider multiple linear actuators, and we note that the strain are in fact non-linear due to the conical shape of the manipulator. So the linear prescribed basis of the generic geometric strain approach struggle to match the shape of the manipulator, as can be observed here. On the other hand, the strain basis of the trivialized approach, which depend not only on the actuator design but also on the rod stiffness, perfectly match the continuous Coursera shape. This trend is even more evident in the second example, where we consider two helical actuators with different pitch, and the difference now between the trivialized model and the generic geometric strain approach are even more evident. And with that, I would like to thank the co-author of this work, Dr. Costanza Armanini from California University, Professor Vincent Lebastard from the IMT Atlantique, Professor Fabien Candelier from Aix-Marseille University, and Professor Frédéric Boyer from the IMT Atlantique. Thank you very much for your attention, and if you have any question, please do not hesitate to send them to me at this email address. Ciao!